Welcome back to another explainer. So, today we're diving into something that's honestly going to blow your mind. We are taking a look at a fascinating study that takes something you've probably tossed in the trash 100 times, a completely ordinary clementine peel, and literally transforms it into the clean energy of tomorrow. We're going to break down the exact science, the thermokinetics, and even the artificial intelligence that's being used right now to turn everyday agricultural waste into a totally renewable powerhouse.
Okay, let's just start by letting this staggering number sink in for a second. 278 million. That is the amount of CO2 emissions, in tons, that Saudi Arabia's Vision 2030 initiative is aiming to cut every single year. I mean, that is a massive, incredibly ambitious environmental goal, and it sets the perfect macro stage for our tiny little citrus hero. You see, to completely escape our reliance on fossil fuels, we desperately need alternative energy sources that are actually efficient. And because of that, every little bit of biomass, yes, including discarded fruit peels, is finally getting its moment in the spotlight.
All right, so here is the roadmap for our Peel's epic journey today. 1. The Waste to Wealth mission. 2. Anatomy of a clementine peel. 3. The fiery trial, pyrolysis. 4. The kinetics of energy. And 5. AI, the ultimate navigator.
Let's jump right into part 1, the Waste to Wealth mission.
Look, we all know the big picture problem we're facing, right? We have to get off fossil fuels, and we have to figure out a smart way to manage the sheer mountains of agricultural waste we produce globally. The framework we're working within here is the circular economy. This is all about the 4 R's: reduce, reuse, recover, and recycle. In this specific context, we're talking about biomass devolatilization, which is essentially just using intense heat to break down waste and recover its usable energy. It's an absolutely crucial tool. This is exactly the kind of process countries are banking on to hit net zero greenhouse gas emissions by 2060. We aren't just chucking things into landfills anymore. We are actually recovering their stored energy.
Moving right along to part 2, anatomy of a clementine peel. Before we can extract any energy, we really need to understand what this peel is made of on a chemical level. What we're looking at is a remarkably high oxygen content at 47.5% and a really high carbon content at almost 44%. This confirms its highly combustible, plant-based, or lignocellulosic nature. But honestly, pay super close attention to that very last stat: 0% sulfur. That total absence of environmentally harmful sulfur means we are not going to be releasing toxic sulfur dioxide or hydrogen sulfide gases during the heating process. It is incredibly, incredibly clean.
Now, here's where the magic actually happens. The real secret to its potential lies in this massive drop in solid carbon. When the raw peel, which has about 42.7% carbon by weight, goes through thermal breakdown, it leaves behind a solid biochar containing only 7.5% carbon. So where did all that carbon go? Well, all that missing organic matter is successfully released as energy-rich, volatile gases. And that is the exact fuel we are trying to capture.
And this totally proves that our little peel is a heavy hitter for bioenergy. It boasts a theoretical high heating value of 15.49 megajoules per kilogram. To put that into perspective for a second, that is a higher heating value than everyday biomass wastes like rice husks or paper. It is a highly reactive material that's basically just waiting to be tapped.
Which brings us to part 3, the fiery trial, otherwise known as pyrolysis.
You'd think if you toss a peel into a super hot combustion chamber for thermal degradation, it just heats up and goes up in flames all at once, right? Actually, scratch that. It's way more interesting. Instead of one chaotic explosion, the thermal breakdown of our biomass is a highly complex, 4-stage process. Literally, peeling back the chemical layers means different structures break down at specific overlapping temperatures. First, we dehydrate the moisture. Then, the hemicellulose breaks down, followed by the cellulose, and finally, at the absolute highest temperatures, the incredibly tough structural lignin degrades.
All right, part 4, the kinetics of energy. To actually harness this fiery breakdown efficiently on an industrial scale, we gotta zoom in on the math, specifically activation energy. Think of it as the minimum entry fee of energy required to break down the peel's robust carbon structures so we can unlock its potential. A lower activation energy means the reaction is way faster and highly reactive. And honestly, that's exactly what makes for a perfect, large-scale bioenergy feedstock.
Since this pyrolysis is a multi-step process, scientists couldn't just rely on one simple equation. They had to use several highly sophisticated model-free methods like FWO, KAS, and Via-Zovkin to pinpoint this energy requirement. And what did they find?
They discovered an average activation energy of around 128 kilojoules per mole for the primary volatile release. In the world of biomass, that is wonderfully low, which absolutely confirms its high reactivity.
And the actual mechanics of this? Fascinating. Out of all the complex mathematical models they threw at it, the defined diffusion model fit the experimental data almost perfectly. What this tells us is that devolatilization isn't just a flash in the pan. It's a solid-state reaction that's totally controlled by diffusion. Basically, the energy release is bottlenecked by how fast the new volatile products can physically push their way through the pores of the solid peel itself.
But this brings us to a literal massive engineering challenge. With all these overlapping temperatures, different chemical components, and super complex multi-step diffusion reactions, how on earth do we predict and optimize this chaotic thermal breakdown for an industrial scale? We basically need an all-knowing oracle to map out the safest and most efficient route.
And that leads us to our final stop, Part 5, AI, the ultimate navigator. Yep, this is exactly where artificial intelligence steps in to navigate this giant mountain of thermokinetic data. Researchers basically unleashed advanced deep learning models to predict the thermal behavior. They used deep neural networks, or DNNs, which are totally fantastic at recognizing complex hierarchical patterns, and long short-term memory networks, or LSTMs, which excel at analyzing sequential data over time. You guys, we are using the exact same technology that powers modern AI chatbots to optimize how a piece of fruit waste burns. Now, training an AI is kind of like finding the Goldilocks zone. If you give the neural network too few neurons, like the 2x2 model, it's way too simple and underfits the data. It essentially just fails to learn. But if you make it too complex, it just starts memorizing the background noise, which is that big problem called overfitting. Well, the researchers found that 2 hidden layers with exactly 10 neurons each hit that sweet spot. It perfectly mapped the peel's thermal features, hitting an astonishing 99.5% accuracy rate. Then there's the LSTM model, which took a slightly different angle. You see, traditional neural networks can sometimes crash and burn during training because their mathematical gradients either explode to infinity or just vanish to zero. To stop that from happening, the LSTM model actually splits its memory into dual pathways, one short-term and one long-term. This let the AI perfectly track the sequential stages of the peel's breakdown over time, and it resulted in a massive 97.8% accuracy score. So what does this all mean? Well, I'm going to leave you to ponder that exact question, because really understanding this single clementine peel's hero journey, from a trash can all the way through complex thermokinetics to being successfully decoded by advanced artificial intelligence, fundamentally changes how we see literally every piece of organic waste on the planet. The solutions to our absolute biggest energy problems might just be sitting right there in your compost bin. Thanks so much for joining me for this explainer, and hey, keep looking for the incredible science hidden in the everyday.